welcome back. So, I will show you, I showed up to 2 rotation. How about 3 rotation? Well, whether it is a 2 rotation or 3 rotation will depend upon the rod like structure. Okay. What is its structure? Let me first write a 3 rotation. Okay. And this one I will not draw the all structure, but I will do away with cartoon, otherwise it will take long time. Okay. So, suppose I have this O benzyl, or I can write OH, hardly matters, OH, then okay, let me, these are actual compounds made. So, that is why I am be little bit careful. 1, 2, 3, 4, 1, 2, 3, 4, 5, and then that aromatic. If you look at your previous structure, you will have some sort of idea. One, 2, 3, 4, 5, 4, 5, okay, and then at least this rod like structure is easy to draw. So, I am drawing. Macrocycle is also easy to draw, but it will take a large amount of time for me. 1, 2, 3, 4, 5, 5. So, I do not want to spend that much time on structures. We have a long way to go. These are just supramolecular synthon. 1, 2, 3, 4, 5, OH. And what happens here, that compound, the first macrocycle that I have drawn today, okay, that first macrocycle will go here. Maybe I will put a different color, it will be easier. Maybe I will put this color. Let me put and you remember the first when I first started this pseudo-rotation structure, the macrocycle I gave, that 4,4 bipyridinium moieties were there too. So, I am talking about that. So, this is one, and another can go here, another will go here. Why they will go here and here? That is because that macrocycle has pyridinium. So, plus both nitrogen are positively charged, that means electron deficient system. Okay. So, these are electron rich. So, they will form pi stacking. Okay. So, this will go 1, 2 and 3. So, this is my 3 pseudo rotaction, 3 pseudo rotaction. Three pseudo rotaction, and if I put a stopper, I can get stopper is when you like it to be difficult for something to come out, then we always do like this. Okay. Stopper I here I write here I should have an oxygen, forgot about oxygen. Okay. Okay. This oxygen must be there, oxygen. So, maybe I will write with this black. And okay. So, you have from 3 pseudo rotation, I made 3 rotation. I made I made 3 rotation like this. Okay. In a similar manner, I can draw this. Remember the stopper. Okay. So, I will let me draw. I think drawing is important. Let me draw. At least one arm I am drawing. I am not, there are 3 arms which I am not drawing. Okay. So, let me draw only this arm. Okay. Writing is very easy, but synthesizing is not. Okay. Remember that stopper and all that I told you, it is valid. Those reasonings, those arguments are valid here also. Okay. No, I messed it up. have tertiary butyl here. How can I? Okay, so you have those. Similarly, you have here, you have here. Same thing, and you had that particular macrocycle. Remember 5 membered, 5 oxygens, not 5 membered, 5 oxygen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay. So, if we cook this one with this one, this is 1 equivalent and this is large, say 4, 5 equivalents, okay, large excess. Here I will write 3 equivalent just for the sake of writing something. Then what will happen? Same thing, MECN, in MECN medium 55 degree Celsius 10 days, and what you get? Now I am drawing, you will understand. So, that is why I am drawing now. This is one, okay, and this is my okay. So, you can form like this, that, and that I will call 4 rhotaxane. 1, 2, 3, and then this unit 1, 4. So, 4 rhotaxane. So, 4 rhotaxane can be synthesized like that. Okay. So, we took lot of time in writing this, in drawing these pictures and how to make it, and what sort of components you will use, so on and so forth. Now, why to do that? I will take an entire class on rhotaxanes. That is a very important molecular machines you can generate. Okay. But I will say here another, a simple example. Let me put, I will this is important that I must draw the entire structure, that is important here. Silicon, let me first draw it, oxygen, again 5, 1, 2, 3, 4, 5, yes, 1, 2, 3 is actually done, it is not that I am making it up, 1, 2, 3, 4, 5, and four, 5, 2, 3, 4, 5, okay, and then the stopper. Stopper, so stopper, stopper, okay, the stopper. What is my, I can draw that also, N N plus plus this also I have to okay. Let me draw properly this, and this I will draw here. Good. Four-foot dash bipyridine, okay, both sides 4-foot dash bipyridine. Now, when you synthesize that, it will come in this part, it can come this part also, but since I am 1:1, only one macrocycle and only one linear. So, this by design 1:1 molar ratio. So, I got only one, that also in MECN 55 degree, 10 days, so on and so forth. So, now if I give it energy in the form of heat, then what will happen? The macrocycle is stationed here. Now, this macrocycle will move and it will be stationing here now. It will come here. So, from here it will come here. Why it will come here? Because we are giving it energy in the form of heat. So, this is what is called molecular shuttle. Molecular shuttle. It is known as molecular shuttle. Like a shuttle, it goes, it moves from one station to the other station. and then again it can come back from this station to this station. So, between these two are as if they are two stations, and this macrocycle is going from here to here and coming back. Okay. So, that is why it is called molecular shuttle. Similarly, there are many molecular machines can be built with rotaxane. If I have, for some reason, if I have a polyrotaxane that I gave you one, suppose I have this, so I make like this and put a one macrocycle here, another macrocycle here, another macrocycle here. Why they will be here and here? Like this, they can be either here or here. Similarly, here one macrocycle is here, one macrocycle here, one is here, and this is known as molecular abacus. Abacus, have you all of you know abacus? People used to use for calculation and all that. Abacus, it can go from one to the other, it is called molecular abacus. Molecular abacus. So, we can make various designs with these rotaxanes and pseudorotaxane. So, we have covered so far the pseudorotaxane and rotaxane. So, now I will go to the another part of this complex structure. I will draw this structure now. Suppose you have a macrocycle, okay. You have a macrocycle, I have another macrocycle inside. So, if there is one macrocycle, I have another macrocycle, they are like this. Okay. When they are like this, then they call catenane or catenand. They are called catenane. Okay. So, they can be, they are very interesting structures. You can make molecular machines with this species also. So, this specifically it is 2-catenane. What I have drawn as a in the form of a cartoon is called 2-catenane. So, after 2-catenane I can write this also 1, 2 and 3. So, I can make this also 3-catenane. Okay. So, I can make 2-catenane, 3-catenane and N-catenane. So, I can keep on making catenane structures. So, I can make N-catenane. N-catenane. They are not very easy to make. So, when I say N-catenane does not mean that 10 of them this will be catenated. Okay. We have, so there is a limit. When you have 5 of this, then we call it Olympiad N, 5-catenane. So, I will draw this structure, how to synthesize them. I will, so this is a very good example of kinetic template effect. Okay. So, let me now go about synthesizing what we will call 2-catenane. Okay. So, what I will do, this is very important, this will be based on, you know already, kinetic template effect. Kinetic, this is really ugly. Kinetic template effect. So, after rotaxane and pseudo-rotaxane, this is another entangled structures, okay, another interlocked structure. So, let me draw, let me say how to synthesize 2-catenane. We can draw that by means of kinetic template effect. So, let me draw. We take this particular compound, (1,10) phenanthroline, this was first shown by Germerilen's student, first student, and he also got Nobel Prize. Hang on. Okay. Here you go. 1, 2 and then 3. Okay. Let me draw the picture completely and then I will explain. Okay. 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 So, first I will discuss why take this to make catenane. If you look at this particular molecule, what does it look? It looks like a rigid structure, rigid, very rigid. So, we take a very rigid structure. If there is a flexible, these two arms will go here and there and we may not be able to isolate catenane. So, number 1 point, we have to take a rigid structure and in the middle of the rigid structure here we have 2 nitrogen that donates to a transition metal ion that can coordinate a transition metal ion, that is number 2, coordination to a transition metal ion. Why? Transition metal because nitrogen. However, transition metal ions, only 2 coordination sites will be occupied. If a metal ion is here, metal ion, only 2 coordination sites are occupied. How about the other sides? To have other sides, I must have another of these at least. If it wants 4 coordination, then what will happen? 4 coordination means I will require another. So, I write like this, another one, nitrogen, nitrogen. Okay. So, therefore, I again go, these are very crucial and each point is absolutely important. So, what happens? I have one, I am putting another, and they has to be like this, okay, and they are now 4 nitrogen. So, if I put a metal here, 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 so that is the criteria number 1, all right. So, because of lack of time, I stop here today. So, again in my next class, I will elaborate on this aspect and synthesize our molecule. Thank you very much.